Hey everybody, this is going to be a video that ultimately lets us calculate the pH of an acidic or a basic solution. But before we can get into that, we need to talk about something that's pretty crazy. And it's actually referred to as the self-ionization of water. Okay, so a few things. We know that water has a pH of 7, right? It is completely neutral. And the reason that it is completely neutral is because if acids have an H and bases have an OH, push that together for me quick, HOH, H2O. Boom. Acids and bases neutralize each other in this way. When you have the hydrogen and the hydroxide, they come together and make HOH or make water, which is why water is completely neutral. It's equal parts acid and base, so they neutralize one another. We'll talk more about neutralizations here shortly as well. But if you remember previously, our definition of an acid is something that produces hydrogen ions, and our definition of a base is something that produces hydroxide ions. So if you think about it, water kind of has both, right? Water has an H and an OH. So water can do this crazy thing, which is called self-ionizing. Basically, we know that ionizing is giving an H to form that hydronium ion. So what water can do is water can just do that with itself. So two water molecules can hang out, and one can give up an H and form hydronium, and then that just leaves hydroxide by itself. Weird, right? We'll talk about the fact that this doesn't happen very frequently here in just a second, but it's possible, right? So one water can give up an H to another water, and then you get hydronium and hydroxide. And then these are going to be in equal concentrations of one another. Remember, these brackets represent concentration or moles per liter. For this to be completely neutral and have a pH of 7, you need to have equal amounts of H and OH in the water for this to be neutral. Because if you've got more H's or more OH's, then it's going to flip to be either acidic or basic, depending on which one you have more of. Okay, so this happens, but as you can see by this Kw number, not a ton. So we've got our equilibrium concentration of K, and we're calling it Kw because W is for water. So the Kw, or the equilibrium constant of water, is 1.00 times 10 to the negative 14th. Okay, that is a small number. And what do we know about small equilibrium constants? That means the reactants are favored, and in this case, way favored, right? Because that number is so small. So not a lot of the water molecules do this. Some do, but not a ton. And so if we've got this number, and also note that this is 25 degrees Celsius, so this is at room temperature. We know that temperature can affect equilibrium, so the room conditions are important for this as well. Let's go ahead and actually just write the K expression. So if you remember, the K expression is products over reactants, and then you take any coefficients and then put the concentration to the exponent of that. So if this is products over reactants, our products is going to be the concentration of the hydrogen, and remember, we're lazy and we know it's actually hydronium, and then the concentration of the hydroxide. And then you do it over reactants. Well, the reactants in this case are water, and if you recall, this was a fine detail, but if you recall, since we're measuring concentration moles per liter, this can only be of solutions, so aqueous solutions and gases. So liquid water isn't a solution, so it actually would not be included in our K expression. So our K expression would actually just be done right now. All right, I told you what K was for water. So 1.00 times 10 to the negative 14th is equal to this H plus times OH minus, okay? Remember how I also said that these values have to be equal? Because if water is totally neutral, you have to have equal amounts of the H or OH, so it's neither acidic nor basic. So if I replaced, let's say, this value with X, okay, but these have to be the same in order for this to be neutral, could this not be X times X? Let's simplify this further. Can this not just be X squared? Okay. Well, if this can be X squared, can we not? That's a triple. Can this not be solved, right? So square root. If you take the square root, you can probably do this in your head. I know the answer, but for the sake of drama, take the square root of that. You get sig figs 1.00 times 10 to the negative 7. And remember what X was, it was the concentration of H plus and OH minus because they have to be the same. So now we know in absolute pure water how many moles per liter there are of hydrogen ions and hydroxide ions. And I bet you're thinking, cool, why do I care? Because, like I said, our ultimate goal here, and I'm going to actually sneak ahead for just a second. Our ultimate goal here is to be able to calculate pH. And here are those calculations for you. Basically, the pH is the negative log of the hydrogen concentration. You might notice that pH, right, it's got the letter H in it. That is because it's measuring the concentration of hydrogen ions in solution. And there's actually something opposite of pH, and that's pOH, which is measuring the concentration of the hydroxide ions. And these two scales, pH and OH, are actually opposites of one another, meaning a 1 on the pH scale is going to be a 14 on the pOH scale. So they work inverse of one another. So like I said, it's the negative log of the concentration of H and OH. What we just solved was the concentration of H and OH in water. So if I take the negative log, let's come back up here. Beep, 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 beep. If I take the negative log of 1.00 times 10 to the negative 7, which I said was my concentration of H, guess what it is? 7. What's the pH of water? 7. Mic drop. This is why we're talking about this. Because essentially, if you can figure out the H and OH concentrations, you can figure out the pH of anything. So on that note, let's do some examples with it. Okay, so like I said, this was at equilibrium, right? This idea of water self-ionizing. So all of these reactions are actually at equilibrium. They can work back and forth. And as you know, if we change the environment of equilibrium, it can actually shift to accommodate that change. And the K value actually doesn't change because the only thing that changes that K value is temperature. So if I'm adding hydrochloric acid to a pure water substance, I'm adding hydrogen ions and I'm adding chloride ions. Those are negative, which means the hydrogen concentrations are going to go up. Now, if that K expression is going to stay the same, if that K value is going to stay the same, even though I'm changing the environment and the H's are going up, by proxy, the hydroxide ion solutions need to go down as a result. So if there's more H's and less OH's, that's what's going to make this ultimately acidic in nature. So here's an example problem I could ask you related to this. If you've got 0.110 moles of hydrochloric acid in 1 liter of water, what is the H plus concentration? What is the hydroxide concentration? So one thing I just want to point out right away is I've got 0.100 moles in 1 liter. And if you remember, these brackets are always representing concentration or molarity, which we know to be moles per liter. So if I've got 0.100 moles in 1 liter, I've got 0.100 molar, right? Because this is to 1 liter. So just something to be mindful of if it isn't 1 liter. One thing that we know is hydrochloric acid is strong, which means it completely ionizes when it goes into water. So if you're putting 0.110 moles of HCl into the water, well, you must be getting 0.100 brackets of your hydrogen ions as a result. And that's your answer for the first part, because this is a strong acid and it's going to completely ionize. If you put 0.100 moles of HCl, you'll get 0.100 moles of H+. So that's the easy part, okay? This hydroxide concentration takes a little bit more work. If you remember, kW of water was 1.00 times 10 to the negative 14th. And that K expression is equal to the H plus concentration times the hydroxide concentration. And that K expression is going to stay constant because we're not influencing the temperature or anything like that. So if I go ahead and just kind of plug in here a little bit, 1.00 times 10 to the negative 14th. My H plus concentration for this particular problem I know to be 0.100. Well, I can then solve for the concentration of the hydroxide ions. So if you divide by 0.100 on either side here, 1.00 times 10 to the negative 14th divided by 0.100. Watch them. Oop, it'd help if I typed that in correctly. Hang on. Calculators, they betray you. I'm getting 1.00, watching my sig figs, times 10 to the negative 13th for the concentration of hydroxide ions. So basically, if you know the concentration of one of the ions, either H or OH, Kw for water is going to always stay consistent at being 1.00 times 10 to the negative 14th. So if you know one of them, you can solve for the other. So now on the flip side, we can do the same thing with bases. So for example, if you're adding sodium hydroxide to water, you're adding more sodiums and more hydroxides, which means obviously your hydroxide concentration is going up. And since this is in equilibrium, if your hydroxide concentration is going up, your hydrogen concentration therefore has to go down in order to keep that K value the same. So why don't you try a couple of these? Okay, so this is going to be very similar to the one that we just did with acids, but now it's going to be bases. So you can easily solve for the hydroxide concentration and then see if you can solve for the hydrogen concentration using that Kw value. All right, so the first one was really similar to the one that we had done together previously. It was just a base instead of an acid. So that 0.010 moles per 1 liter is the concentration. Strong completely dissociates because it's a base, so then you can just solve for the H+. So that's how I got the 0.010 and then the 1.0 times 10 to the negative 12th. And the next one, not that I was like trying to trick you per se, but there was a detail here that you needed to kind of catch. Notice that calcium hydroxide has 2 OHs. Okay, basically that means if you put 1 calcium hydroxide in the water, you get 2 hydroxides as a result. So if you wrote like the dissociation equation, for example, you would write 2OH. So this is saying I've got 0.10 moles of the calcium hydroxide. Well then, for just the hydroxides, because that's the part of this I care about, I would get double of it. So that is why my hydroxide concentration is 0.20, because I'm going to have double the concentration of OHs, given the fact that there are 2 of them in the compound. So that's why I plugged in that value. Oops, I wrote the wrong number, which means this is going to be a different answer. Hold on. Shh. That's the answer. Okay. Beautiful reminder. Always check your work because it's very easy to write the wrong number. So getting to the point of calculating pH and pOH. As we know, if something is neutral, the concentrations of the H+ and the hydroxide need to be equal, which is a pH of 7. If it's acidic, there's more hydrogen ions, and that means the pH is going to be less than 7. Basic, there's going to be more hydroxide ions, and then that means that the pH is going to be greater than 7. So the pH scale is probably what you're the most familiar with. And if you notice, now we're going to talk about the pOH scale, which is the exact inverse of that. And really the only difference is, are you calculating the concentration of hydrogens, or are you calculating the concentration of hydroxides? So here are your equations in order to solve for pH, pOH, and then also to work backwards. And if you've got the pH or pOH, to go back to the original concentration. Not much to say about these other than, boom, here you go, write these down, commit these to memory, use this as a crutch for now. Basically just take the negative log of the hydrogen to get pH, and then to go backwards, take 10 to the negative pH to go back to the hydrogen ions. So let's just kind of start filling out this table together, and then I'll let you try it on your own. So for example, this is hydrochloric acid. So if I've got this concentration of it, I'm going to have that many hydrogen ions in solution. And let's just skip ahead to the pH to try that really quick. So remember, you're going to do the negative log of the concentration of the hydrogen ion. So in that case, that is going to be 2. With a pH of 2, we know that this is going to be an acid. To figure out the OH and the pOH, what you can do is use that Kw value of 10 to the negative 14th and solve for the concentration of the hydroxide ions, just like we were doing before. And that is 1.0 times 10 to the negative 12th. Once you've got that value, then you can just take the negative log of that value and get the pOH, which would in this case be 12, because it's going to be the inverse of it. Go ahead and try filling out the rest of this table on your own. All right, here you go. You probably were able to identify a pattern